Okay, morning everybody. My name's Brian Holman. I'm going to be giving the lecture today. The intro to the lectures, for those of you who don't have a background in aerospace, there's some information on airplane engines, and then the remainder of the lecture is going to focus on basically a case study of an accident of a flight in Sioux City, Iowa back in the late 80s. Just for the video for the guys coming in, Steve Lyons is going to be lecturing the remainder of this week, Wednesday, Thursday, and Friday. And then next week, he's going to be giving his final 3 lectures on Tuesday, Wednesday, and Thursday. So there won't be class next Monday or Friday. Basically, the lectures will be finished, the live lectures will be finished next Thursday. So a little background on critical airplane engine components. Okay. Everyone in here has been on a flight before, correct? So one of the things you don't realize is the harsh operating environment that the engines experience while you're in the flight. You're dealing with high temperatures in the turbine section above the melting point of the alloys used, as well as high atmosphere pressures and issues related to velocity and vibration of the turbo machinery. So what we see here is the general sections on the engine. You have the inlet section where the air comes in, and then you have your fan blades. You have a compressor section, which consists of both LPC, low pressure compressor, and high pressure compressor. And then from there, you have a combustion chamber where ignition actually occurs. From the combustion chamber, it goes into the turbine section, which is where the thrust in the engine comes from. And from the turbine section, it then goes from a high-pressure turbine to a low-pressure turbine and out the exhaust. So the example shown here was for a 2-spool engine, which deals with how the engine actually rotates. And this isn't an aero-astro class, but there are whole classes on engine design. And one of the things to be cognizant of is that the speed at which the engine rotates and the temperatures at which you want the turbine inlet to reach all deal with the efficiency of the engine and all have constraints. So for a 2-spool engine, you have constraints that the various spools have to operate independently but together at a fixed ratio. You have to understand that there's mass flow constraints, power and energy balance constraints between the compressor and turbine sections. And if you don't have those, what can happen is you can either get surge or stall conditions in operation, or you can get vibration. So for the compressor section, it's the aerodynamics. What happens is you have the air come in, you have to actually compress it through the various stages of the LPC and HPC. And then at that point, when you go into the turbine after combustion, it's the turbine inlet temperature that drives the efficiency of the engine. You want to get as high as possible turbine inlet temperature so you can get the best efficiency overall in the engine. And this is actually now they're at the point where the turbine inlet temperature is above the melting point of the nickel-based superalloy or the whatever alloy they typically will use in that section. But if we're looking at this chart here, what happens is from the various sections, right? So as you have the inlet through the fan section, you're at a low temperature and low pressure. As you go through the LPC, which can be the total number of stages between the low pressure compressor and high pressure compressor is typically 12 to 19 stages. So if you had 12 LPC stages and 7 HPC stages, through each one of those stages, you have both temperature rise and a pressure rise, to the point where it then goes into the combustion chamber, ignition occurs at about 40 atmospheres, and this is in degrees Celsius, but it's over 2,500 Fahrenheit. That's where your ignition occurs. And then as it goes through the turbine section is when the work is done on that section. Work is done on the engine in the form of thrust, which runs the engine. And as it goes through the turbine section and out the exhaust, there is a drop in both temperature and pressure. And just one other thing. This image here shows various material selection options in the various sections of the engine. So what you'll see is in the turbine section, a lot of times you'll have what's called nickel-based superalloys because they are able to withstand the high operating temperatures and pressures, and they have good oxidation resistance in that environment. In the fan and compressor sections, you'll either see stainless steel type alloys or titanium base alloys, with Ti 6Al4V being the most highly used alloy. So what is a critical part? So the FAA, Federal Aviation Administration, defines engine life limited parts, LLPs, as rotor and major static structural parts whose failure is likely to result in a hazardous engine effect. So hazardous engine effect, it means uncontained engine, which means that some part, whether it be a disc, a blade, or vane, or another engine part, can actually pass through and be released from the engine in operation. They also have contained engine events, and Professor Iga had mentioned that in one of the previous lectures. Something like that can happen, and you might not even know it happens during a flight, and it might just result in them shutting down that particular engine. Whereas if you have an uncontained engine event, the NTSB will get called in, and there'll be a large investigation, because oftentimes when you have an uncontained engine event, it results in catastrophic failure, and more times than not, fatalities and critical accidents are involved. So one of the images here, I believe this was the nose of the plane after the Pensacola, Florida crash. A couple more images. A lot of these images are taken from NTSB when they're on site to do their accident investigation and reconstruction. So what you're seeing here would be a fan hub section that has a complete fracture and was released. And there was on the news a couple weeks ago, I guess the cover to an engine came off during flight, and the news was showing the engine vibrating back and forth. What happens when something like this happens is a lot of pieces in the engine can be released, and oftentimes they either have to scrap the entire engine, which is millions of dollars loss. So the industry data has shown that manufacturing-induced anomalies, so in the forging and casting processes themselves, account for about 40% of the rotor cracking events for data up to 2010. And the FAA, every 6 years or so, puts out a report on a whole list of uncontained engine events and what was their cause, the location, and whether human factors, things like that, were involved. So about 40% of those deal with manufacturing-induced defects in the fabrication of the component. So an uncontained engines rate, I don't know if it's gone up or down since then, but there was about 3 events per year from data from 1984 to 1989. Material issues, which has become less of a problem since they've gone to triple melt practices and vacuum arc remelting. Manufacturing issues, maintenance issues. Most of the plants have improved since the 80s on those issues. So because there was some critical catastrophic failures in the 80s, What happened was the FAA decided to set what's called a safe life approach to these critical parts, meaning that whether they still had useful life left or not, they would have to be retired from service based on X amount of cycles that they were reached. So it wasn't retirement for cause, meaning that the component, the alloy had basically reached its end of its life due to the environment. It was retirement based on a preset number of cycles that the engine would reach. And they in their fracture mechanics calculations, they use the 0.03 inches long by 0.01 inches deep as their input to determine what number of cycles would be allowed. So the lifing methodology requires coordinated engineering, manufacturing, service, maintenance plans, because you have various numbers of life-limited parts. They're manufactured from different alloys, and based on cycles and based on the mission profile of whether you're doing little jump flights, 1-hour jump flights, or whether you're doing 16-hour, flights halfway across the world, the mission profile and the environment the parts undergo will affect how often maintenance has to be performed on them. So one of the main things is control of the grain structure and microstructure, and this relates to nickel-based superalloys as well as titanium-based alloys, is the primary determinant of the manufacturing properties while it's in service. But what happens is, at least in the turbine section, because you're operating at such a high temperature, there's ways that the airplane companies and the OEMs, which is original equipment manufacturers, because that turbine inlet temperature is so high, they've had to now design more and more intricate methods. So this is a turbine blade here. What you'll see is they actually laser drill in cooling holes. And Professor Eager, I think in one of the previous lectures, showed one where you can open it up. And you have various cooling passages that run inside this blade. So air actually comes in and passes through to cool it while it's operating so it doesn't melt in service. The other thing that they do on the turbine blades is they put what's called a TBC, a thermal barrier coating, which is a ceramic-based coating, and that also has laser drills put through it because you're operating beyond the melting point of the nickel-based superalloy. So you can pass that along. The other thing on here, this is a duct segment. What you'll see is when they do non-destructive testing on it, they'll either do, for this, they'll do eddy current tests. But what you'll see is this part got rejected and for a crack above 20 thousandths. So we're not talking about really large cracks like you'd see on structures, whether it be a bridge or something else, where you actually can tolerate larger cracks. For airplane engine sections, you want these parts will get rejected if the cracks are thousandths of an inch. So the processing steps are key when and we're talking each one of these blades is probably $5,000, and because the high alloy costs, you have hundreds of blades, you have multiple sections, right? So we talked about each stage has 100 blades approximately, and each one of those blades is $5,000 to $7,500. So it starts adding up, and an engine, the engines on an airplane are about 20 to 25% of the total cost of the structure. So you have to make sure you have appropriate melting procedures, forging processes, heat treatments. All these things come into play. And if any one of them have upsets involved, they may have to reject these parts, and they're high value parts, so rejecting, high reject rate is unacceptable for the owners and operators. In terms of the failure modes, for these these types of engine components, very important failure modes to consider include high cycle fatigue, low cycle fatigue. So every time you go up on a plane, you have a takeoff, you have cruise, and it goes through its various mission profile up to landing. So what happens is you have a pressure and depressure, which is a cycle. So every time you're on a plane, it undergoes cyclic stresses. So you figure these planes operate for, basically nonstop. It goes from one location to the next. It starts acquiring cycles. So both high cycle fatigue, low cycle fatigue are very important, as well as creep, because we're dealing with high temperature mechanical degradation. So you have thermomechanical fatigue due to temperature gradients and load variations. And just as an example, on a disk hub, the temperature can vary from 300 degrees at the hub to over 1,000 degrees at the rim. So if we're talking on a disk section, even on a single disk, you have between the radial direction over 700 degrees temperature gradient in service. And what happens on these disks, what we'll see here is the manufacturing, it's very critical. This is your dovetail attachment that that turbine blade actually has to fit in. Every turbine blade goes into one of these dovetail attachments. So the tolerances are very tight, because if you have manufacturing issue from the milling process, that will be a stress concentrator, and you'll start getting cracks at the dovetail attachments. So one of the things they design for in the disk sections is what's called the burst speed, which is the speed in your design input at which you have to prevent against the disk actually fracturing and bursting while it's running. That is typically about 1.3 to 1.4 is the factor that they use beyond what the design speed. So you do have safety factors already accounted for, but the components operate at pretty aggressive temperatures and pressures, and they really push the limits of the design over the years. So titanium alloys, this relates to the Sioux City, Iowa incident, which was a fracture of a titanium component. Titanium alloys are allotropic, which means that they exist at more than one crystallographic phase, depending on which temperature you're at. So at room temperature, they're hexagonal close packed, and this is what's known as the alpha phase. At around 1620 Fahrenheit, there's a transformation from the alpha to beta phase, and the beta phase is body-centered cubic. So the titanium alloys actually change their structure depending on what temperature you're at, and this needs to be accounted for in your heat treatments and the forging and casting processes that undergo. When you have, we'll talk about TI-64 because it makes up about 60% of the total titanium base alloy production. But what happens is you have to add stabilizers because titanium alone won't give you the properties you need. So what happens is you start adding what's called alpha stabilizers and beta stabilizers to give you mechanical properties, to give you oxidation, corrosion resistance, and other various properties that are needed in service. So the alpha stabilizers include aluminum and oxygen, and the beta stabilizers, vanadium, molybdenum. And what happens is, as you start adding more and more alloying elements, and this is the same as true for nickel-based superalloys, it gives you more and more opportunities for localized areas of concentration where you can ultimately get brittle failure inclusions or other issues if you don't do your forging, casting, and heat treatment appropriately. This image down here, it's what's called alpha case. So what happens is on a TI-64 alloy, you get oxygen diffusion into the alloy. And what happens is oftentimes they'll get this rust-looking appearance on it, so they have to mill that off. So you can see a distinct difference between the alpha case region and the region that's been machined. And all these things have to be taken into account, and especially for people who work in the manufacturing facilities, because you don't want to leave material just laying around, because you'll have oxidation reactions that are undergoing. So getting that, ties into people who do the supply chain and the movement of the material through the plant. So one of the issues with TI-64 is you have an inherent microstructural variability of the alloy itself, because you have two various phases. You have an alpha phase and beta phase. And what we're seeing here in these micrographs are, if you look closely, you can see these are grains. So there's various grains here, and what you're seeing is this is beta grains, the darker colored, and the lighter colored are the alpha grains, and they're distributed in various proportions depending on the chemical composition and just the manufacturing processes. And you're always going to have variability from one batch to the next. So these are things that you can't really design against. You have to just take into account when you're doing mechanical properties. You have a range. It's not just a single value. And you have to understand that if you have isolated regions where there's either all beta grains or all alpha grains, that's not wanted. You want a random dispersion of the grains throughout the structure. One other thing just to point out, for the titanium alloys, it's what's called a Widmanstätten structure. It translates into a basket weave structure. And just a little metallurgy, since we are in a material science class. For the nickel-based superalloys, some issues. Segregation is the main issue in the forging and the melt processes that are critical for the nickel-based superalloys. What happens is, as you have a large ingot or billet, as it cools, the outer part of the billet will cool at a different gradient than the inside part. And what can happen is, on a large structure, whether you're in the center or on the ends, you can have segregation that occurs if it's not controlled if it's not cooled in a controlled manner. So what happens is, what you can get segregation, it results in various grain sizes. And so what they do typically with nickel-based billets is a process called hot topping. So they know they'll get segregation based on the cooling. So they decide that if we can control where the segregation occurs, we can then remove that, and basically that goes back in and they remelt it and reuse it. So it's a process called hot topping. They take off about 7% from either end, where they expect the segregations to be. But now if you have an upset condition in the plant and you have segregation somewhere else that you don't expect, after you do your hot topping process, you can get other issues, which could include carbonitrides, which are slag stringers. White spots and freckles are various forms of segregation. And what you see here is just some SEM images of white spots and freckles in a nickel-based superalloy. And porosity is another issue due to diffusion effects. So for titanium alloys, there's two main types. So the type 1 defect is called a high interstitial defect. And this is an alpha region that has a higher hardness than the surrounding material. Now, one of the things that happens when you have a localized area of high hardness or not, that's where your crack initiation will occur. So you want to try to avoid having brittle regions in these components that are spinning at 20,000 RPM and operating at 2,000 to 2,500 Fahrenheit and high pressures. because if you have a brittle region, it often will end in a catastrophic type fracture. So the brittle region in the high interstitial defects are often due to localized nitrogen, oxygen, or carbon components in the alloy melt. This is also known as hard alpha inclusion or low density inclusion. The second type is the high aluminum defect, which is an aluminum-rich alpha region that is over multiple beta grains. So depending on whether you have the alpha grains or beta grains, because you have various stabilizing elements, you'll have different types of defects when you look at it under a microscope based on the elements in each one of those defects. The third one is a high density inclusion. This relates to refractory elements in the melt. So just a quick slide on in-service damage for blades. And you'll actually see an image in the next slide. So you can get multiple types of damage degradation mechanisms while these things are in service. And that's why every couple of years they will do a full teardown of the engine, and they'll do a visual. They'll often do penetrant inspection to try to determine if they have to repair the blades before they put them back on. So locations on various types of degradation mechanisms, you can get nicks and dents on the oftentimes the leading edge due to foreign object damage. So if they actually on the engines, before they certify an engine, they'll do various tests. So they'll do an ice test where they put ice chunks through. I have a video where they throw dead chickens through the engine, and they do a chicken ingestion test. And if you guys seen the Miracle on Hudson and Sully, it actually happens. You have bird strikes when you operate in rough weather. These things are going through the engine while you're going through the air. So you have to design against it. So locations for foreign object damage, tip wear, oxidation, and corrosion are a big issue. What happens over time is the thermal barrier coating, which is only microns to mils in thickness, it will wear away over time just due to the harsh environment. And once the thermal barrier coating wears away, you can then get corrosion and oxidation. And once it initiates, it propagates fairly quickly. Issues, you can get cracking at the root section and the dovetail connections. You can get creep cracks, mid-thickness of the blades and vanes, as well as knife edge sealant loss at the shroud interface. Yep.
Creep growth, is that critical tolerance?
Yeah, because what happens is a lot of times these blades are made from a single crystal process. They're either columnly elongated or it's a single crystal. So that's why you often see, because creep is temperature-based deformation, and you'll see it in the mid thickness. So different degradation mechanisms have different hot spots. So foreign object damage is often on the leading edge because it's a real thin edge. All right, tip wear, oxidation, corrosion is often at the tip here, and then creep is oftentimes like mid thickness of the blades. So different locations have to be evaluated for different degradation mechanisms. And what you'll see is this was actually taken out, well, it was taken out of an operating plane. What happened here is the thermal barrier coating wore away, and a mechanism called sulfidation occurred. This was related to the crude. It was related to where the petrochemical was located, the environment for the gas that they got. It affected the rate of corrosion for this particular engine, but This was operating for multiple cycles before they pulled it out. Most people don't realize that the engine can withstand these types of defects in service. But this is one of the reasons why the FAA has gone to the safe life methodology. It's based on low cycle fatigue. Low cycle fatigue ties into trying to design against a brittle fracture mode. What you'll see is, if you look at U.S. Air Force durability reports or FAA design-based reports, a lot of it's based on empirical observations. So, you know, the various OEMs have numbers that they've used. And one of the things is, as the engine design changes, you have to see whether those empirical observations need to be adjusted or not. If you're changing from nickel-based superalloys to another type of alloy, or if you're then changing wing designs, fuselage designs from metallic components to carbon fiber or other types of components, all these things are intertwined together in the design of the engine. So the empirical observations, I guess they change based on each aircraft has different ones. So as the aircrafts have progressed, the observations and fleet-wide numbers change. As of 1999, and these numbers have gone up quite a bit since 1999, the number of U.S. and European aircraft was over 25 years old, 2,100. I think that number is significantly higher today. And just at the time, it's rule of thumb, about 20,000 U.S. domestic commercial flights every day. So we're talking, there's a lot of parts up in the air. If you guys have ever watched the news where they show the flight tracker, it's, you know, just looks like a whole bunch of dots in the sky at any one time. So what do they do to prevent against those types of degradation mechanisms and defects? Oftentimes they'll just, when the parts come in, they'll do a visual inspection. That's the cheapest way. It's the first line of defense. It's has limitations, though. You can't detect internal flaws. So if there was a flaw on the inside of the turbine blade rather than on the surface, you wouldn't be able to see something like that from a visual. If it was an issue in one of the cooling passages, you can't see that with just a visual. There's also a limit of detection based on the inspector that they use. Basically, they say it's 1/4 of an inch. Now, there's variability from inspector to inspector, so there's a range to that. But the limits of detection that they use as their inputs in the design for fracture mechanics and other calculations is about 1/4 of an inch for a visual. They often do, in conjunction with just a regular visual, a penetrant inspection. So FPI, fluorescent penetrant, LPI is liquid penetrant. So they will spray the component with the developer. It operates by capillary action. And then with fluorescent, they'll put a black light over it. And if you have a crack, it will light up, and that's your indication. Fluorescent dyes render indications of cracks, other surface under UV light. So one of the things is it's fairly inexpensive. You can perform the inspection on complex parts such as blades. You can do it in the root section. You can do it along the thickness of the leading edge, trailing edge. One of the things is it takes time. If you're doing a penetrant inspection, oftentimes you have to let it sit for 20 minutes to allow the capillary action to go into what may be a crack or not. It takes about 20 minutes. So the whole test takes about 30 minutes. The setup, the prep for the test, the letting it sit, and then putting the black light or whatever over it, it's about 30 minutes. So the time is one of the big disadvantages. Sensitivity and reliant on inspector is another big disadvantage because of the variability involved. So I guess the main point is there is no one single bullet NDE technique they can use. So they try to use multiple techniques. They can do ultrasonic inspections for subsurface defects, but when these things go in for maintenance in the plant, they have to perform these things before it'll be allowed back into service. So this comes to United Airlines Flight 232, the case study. What happened, and what we're seeing here is the cover of the NTSB report. And for you guys who have to do research or work in the aerospace industry, NTSB publishes for any uncontained event. They have various categories that they listed under. So Category 3 and Category 4 deal with when a engine component's been uncontained and is released. And for each one of those, they write one of these reports where they'll give you the background and they give you root cause and ways to mitigate future issues. So this is the NTSB report for this particular incident. What happened was there was a catastrophic failure of the stage 1 fan rotor. And why this is such an important case study is when the fan rotor fractured, and you'll see it in the next slide, it resulted in the loss of all 3 hydraulic systems that controlled the flight controls. So when that happened, the hydraulic lines were severed or fractured, and the pilot no longer had control that, whether he could control through thrust and lift. What he had to actually do is do it manually since he lost his hydraulic controls. What happened was upon the crash, there was 111 fatalities. There was, I think, 275 people on board, not including the crew. So about another 11 crew members and 275 passengers. Out of that, there was 111 fatalities and I think another 75 or so critical injuries. So that was a very significant event in terms of loss of life. It was a General Electric aircraft engine, CF6-6 engine design, and that's where the rotor came from. The part that fractured was not found until 3 months after the incident, and some female farmer found it on her property. So one of the things is when the NTSB has an accident, they have an area that they'll comb for evidence. Because this was an uncontained event, they didn't know where to look for the rotor, which was the critical piece of evidence that they needed in the investigation. And 3 months later, a woman's on her property and found it. And what we'll see in the slide after this is related to the hydraulics. So what happened was when the rotor fractured, the loss of the disc as it came uncontained through the engine, that's where it severed the 2 hydraulic lines, and the actual force of the fracture caused the other hydraulic line not in the near vicinity to stop operating as well. So they lost all the hydraulics, and the pilot had to manually, based on thrust and drag, is how he just did it by feel to bring the plane down. So the fact that anyone survived, it's pretty incredible that he was actually able to save anyone's life. So this was the disc section that was found 3 months after the incident. It was found, what you'll see is basically it was in 2 main sections. There was a small piece that was missing that they weren't able to recover. But what we see when we do failure analysis and root cause evaluations is, all right, you either look for something that's a brittle fracture where you can almost mate the 2 pieces back together, or you'll have something where there's ductile fracture, where there's plastic deformation and the whole part is warped. And these things all give you hints as to what the cause of failure was.
I'm sorry, so this is a failure of one of the fan blades?
No, this is the disc. This is the disc right here, and these are where the blades, some of the blades were still on. These are the fan blades. No, this was the fan. Yeah, this was the first stage fan. So that means when that was uncontained, since it's the first stage of the fan, it had to go through all the other sections, which means that there was a lot of subsequent damage to the engine.
DC-10, so it was
It's in the back.
third engine in the back.
Yeah, yeah.
How do you know it didn't fracture when it hit the ground or something?
Well, that will be the subsequent slides when we look at, you actually, that's when you'll look at the fracture surface and you'll do metallurgical evaluation to determine that. But there's two principal fracture areas. So the first one has this circumferential around the hub feature, and after the circumferential fracture, then it goes through the progression through the web and the rim. The second fracture region's almost a radial fracture, meaning that it doesn't go through this tortuous path, around the hub. It was basically, you have your bore, which is the innermost, then you have your web, then you have your disc and rim, and it's almost radial, almost a straight line right through. So how we, this is just some information from the NTSB report. What happened was final fracture was consistent with overstress, but it started at multiple fatigue cracks. So the multiple origin areas, those are often called ratchet marks when you look at a fracture surface, and you can see rather than one single area, you have multiple origin locations, and they, off various fatigue cycles, they will grow and then meet up, and then you'll get to a critical crack size. Once you get to the critical crack size, the cross-sectional thickness is no longer such that it can withstand the operating stresses, and that's where your final fracture, it'll be a fast fracture, and that's where the overstress fracture is observed. This is the write-up from the NTSB report. So what they found from the fractographic, metallographic, and chemical analysis was that it basically came from a hard alpha inclusion from the manufacturing. So the hard alpha inclusion was the origin, and from that it initiated a fatigue crack that grew, and it grew to a critical size, and then overstress occurred. The key thing is that since it was from an inclusion from the manufacturing process, the NTSB report find that from the first cycle, the virgin flight of the plane, that's where the crack initiated on the very first cycle. And it went through multiple inspections where this was missed.
What's the RPM of the rotor that was involved in this?
I'll say, as a rough guess, 20,000 RPM, but if it's the fan section, it might be less than that. So 10,000, 20,000 RPM. The report would call it out, but they're spinning pretty quick. So this is your fracture surface. This is how you know it didn't happen upon impact with the ground. When you do a root cause evaluation, you'll get the fracture surface. So when they're talking multiple origin locations, you would look at this cross section here, and you'll see the ratchet marks here. So this is they progress in what's called beach mark formation. So it actually goes in a thumbnail fashion. Couple of these that I'll pass out. So what you would do is you'd take a metallurgical mount, and then you'd look at this under an optical microscope, and you'd lay it down in such a way that you can look at the surface. So what you're seeing in these two that I'm going to hand out is, one is a weld with some lack of penetration in the weld, and the markings on the various sections are micro hardness markings. So with the hard alpha inclusion, what it led to was a brittle region that would have local high hardness compared to the rest. So what you could do then to confirm whether it was an inclusion or not, you could do micro hardness on the part, as well as just by the visual features of the thumbnail crack, fatigue crack. So what happens is you have your origin region here. This is fatigue progresses to the point where you have final fracture through the remaining cross-section of the fracture surface.
Any way to tell the time?
Yeah, well, they can estimate if they go to a high enough magnification, because it's cyclic, they can say they can see striations, but you can see cycles. It's to try to back calculate an exact number of cycles. It's difficult. It's easier to actually just go into the maintenance logs and the operating logs, because that they'll keep track of the hours the engine's been running that way. So some key NTSB report findings: that the hard alpha metallurgical defect was formed in the material during manufacture from the ingot from which the disc was forged. All right, the defect was missed not only by ultrasonic inspection, it was missed by a macro etch inspection that was performed at the GE facility. And the reasoning in the NTSB report why they missed it was because they did the macro etch in the supply chain, or in the inspection process. The macro etch was performed, I guess, upstream of the critical location where it should have been done. So they did the macro etch at one part, and then the part progressed through the plant where subsequent machining operations were done. The macro etch should have been done after those machining operations, and that's why it was missed, because of when they did the macro etch, not the process of the macro etch itself. The other key thing is that liquid penetrant was performed only 760 cycles before the catastrophic failure, and the liquid, they allowed it to go in even though they noticed discoloration on the liquid penetrant. So this is a key case study, because the FAA, as a result of the number of fatalities and the criticality, really went and changed the processes, both quality assurance, quality control, and the non-destructive evaluation processes that had to be performed in the plant. The hard alpha defect cracked with the application of stress during the first initial exposure to thrust. So the first takeoff is when the crack initiated. As I said, fluorescent penetrant was performed only 760 cycles to failure. It was still allowed to go back into service. And that one of the findings in the report, they noticed in the area around the inclusion there was discoloration, and the discoloration was attributed to the penetrant, what they use on the penetrant. So that was actually fairly damning conclusion that led to quite a few changes to the quality assurance, quality control in the plant. So a quick cost benefit. So there's insurance. You deal with failure like this, you have insurance issues after the fact, and it's how do you quantify losses and things like that. Some $2009, so an in-flight engine shut down, about $500,000. A lot of these things you can get from either FAA reports, there's advisory circulars, but some of it is from airline transport associations or other aviation industry groups that publish these values. What I had done as part of my thesis was do a cost benefit related to missing indications in non-destructive inspection alone. So what I found was in the period 1989 to 2009, there was 3 or 4 commercial accidents that could be attributed directly to non-destructive testing, either missing or improperly performing the inspection. So depending on what year it would occur, you try to put everything on an apples to apples basis. So we're talking the same dollars, right? Same net present value of money. So you have past dollars, future dollars. You have to take into account interest rates. You have to take into account the consumer price index, which is related to inflation. So a lot of these numbers you can get from the Federal Reserve that they change every year, like the inflation rate changes. So, and then this value of approximately $1.5 million for a life, that's the value that the Department of Transportation estimated a human life was worth in 1996. That number can vary greatly depending on who the person is and the potential loss of future earnings. So I guess for the Sioux City, Iowa case, it was basically an order of magnitude. Like one individual, they placed $15 million on, whereas the average is about 1.5 million. So if we look at the 4 incidents in that 20-year period, you have Sioux City, Iowa is by far the most catastrophic of them all compared to Carrollton flight, Value Jet, and the Pensacola crash. 111 fatalities, 47 serious injuries. So taking into account all these costs associated with injury, loss of the aircraft, engines, and things like that, this number trumps far and away, was over 80% of all the costs associated with in that 20-year period. And those 4 were due to non-destructive testing issues. There was a lot of other events that weren't included in this. So the last slide is just on peripheral costs. Litigation costs can be 10 to 20% of that final number, which that's not taken into account. You have damage to the airline's reputation resulting in loss of revenue. And it was estimated that in the Value Jet incident, there was a $55 million loss in sales in the 7 months following that Value Jet crash, just due to people not feeling comfortable flying with it. The public perception resulted in significant loss of revenue, sales revenue. And ultimately, there's been catastrophic failures where the airline has rebranded and changed its name. So you don't hear about Calm Air anymore, right? Or other certain companies, as a way to deal with the poor public perception, they'll change the company name. So that's the last slide. If you guys have any questions, let me know. We're at the end of the time here, so. But if you have questions, I'll take any questions you have.